Next speaker will be Professor Per Stenstom, the endowed chair professor at Chalmers University in Sweden.
Thank you, yeah. Good. Okay. Good morning, and very happy to get invited to this remembrance event of Stamatis, and of course I accidentally have the same excellent photo of Stamatis. I got to know Stamatis more closely when some of us here in the room founded the High-Peak Network of Excellence. Matteo, Manolis, Georgi, where are you? And as a humble, Scandinavian, I was in all these meetings and couldn't really speak out, for, these very, the Mediterraneans that used to basically take the whole show. And Stamatis, at some point I got a little bit angry and spoke out, and then Stamatis said, "Wow, we have transformed you into a Mediterranean. That's great." So I like to start this talk by actually what I found make computer architecture especially interesting today, and that is that all the good trends, they seem to have faded away, and the last one that we hoped for, getting twice as many transistors with each new generation, is also gone now. So what's really exciting is that we will have to make twice as good use of the available transistors with each generation, because we cannot rely on Moore's law anymore. So that's going to be the driver for what I'm going to talk about. And connecting it to Matteo's talk, really what is the problem of the classical way of thinking is, of course, that we have this transformation hierarchy where we hide the details of the next lower level here. So what I like to do is to basically drill through the layers and explore what we could do if we could make the layers interact. And to zoom into this picture, what I'm particularly interested in and what we have been working on over the past few years is actually also based on all the great research in Barcelona, the interaction between Pallet programming models and the runtime, which I call here resource manager, and the architecture. Looking at, in the past where I come from, I certainly spent a lot of time on cache coherence, and that was one thing that Stamatis used to tease me about, cache coherence. Why are you interested in that? It just scales to a few cores. So we're looking for scalable architectures here, and cache coherence is certainly not going to scale much. Anyway, so I zoomed into that early on during my PhD studies, and then that transformed to a number of PhD students in the beginning of my career. And then that took me to more look at parallelism more broadly. And then Matteo and all his great team in Barcelona, they came up with task-based Dataflow programming models. And we started to really look at that as a great opportunity, because as Matteo pointed out, what happens in the runtime system is that it's going to dynamically construct the data flow graph. And what is interesting with that is that there is a lot of information that is kind of can be extracted easily from the Pallet programming model by the programmer, So in fact, writing Pallet programs, the difficulty is not really to divide it into tasks. The difficulty is, of course, to manage parallelism at runtime, right? So the goal for the runtime system and where it should offload the programmer is to actually manage the task in such a way so that we can transform, twice as many cores into twice as high performance, or according to Gustafson's law, go for twice as big problems in the same amount of time. And with my background on cache coherence, of course, with these annotations, as Matteo pointed out, you can do a lot of great things, and I'm going to zoom more into it than Matteo was doing in this talk. So we have basically expressed here the dependencies between tasks and what data structures that they are working on. This is basically what has come out of Barcelona Supercomputing Center with these annotations, output, input, in, out, and so on. So these program annotations can be used to for a number of things that we have looked into. So I also agree with Matteo that the view here is that runtime is part of the chip, you could say, and should manage basically the microarchitecture in an efficient way. With this, what we have zoomed into and looked at more in detail is what I would call cross-stack cache management, where we can, on the one hand, get information from the programming model level, but also dynamically collect useful information as we run the program to do more effective cache management. In fact, this is, one can do an analogy to the responsibility of the OS, where the OS is managing the virtual memory, right? So here, the runtime is supposed to manage the on-chip cache hierarchy, you could say. So we looked into cache coherence optimizations. More recently, we looked into deadlock cache management, and that led us to realize that, wow, there is some real power here called global, what we call global cache management. I'm going to talk a little bit about these opportunities here. Runtime guided cache coherence. There was the debate many years ago about the message passing versus shared memory, right? And the good thing about message passing is that you explicitly define what data is going to be transferred between a producer and a consumer, for example. And we have that in these annotations as well. So what is the good thing is that you can really use the annotations to really instruct the cache coherence substrate more efficiently to send a whole data structure instead of, as cache coherence, it works on the block level, right? But you can do a lot of other things, forwarding, prefetching, as Matteo pointed out, and also something that I invented back in the 90s called migratory sharing optimization. With these annotations, you can do that. So we looked into all that and could see a lot of opportunities in doing that. There was a paper coming out in 2014. But we took it a little bit, then we started to look into deadlock cache management. The problem with the deadlocks is that, I mean, if you take a snapshot of the cache content, a lot of the blocks in the cache will be dead, meaning that they will not be accessed before they are evicted from the cache. And with the information you have dynamically that the runtime system establishes is basically you can look into the future. You have a data flow graph, then you can look into the future. You have a limited view of the future, you could say, to see which data structures will be accessed by different tasks. And this information can be used to basically, let me see if it works here, to be more precise in the deadlock, in detecting deadlocks. So basically, state of the art there was predictors. I mean, using information from the past rather from the future to detect deadlocks and get away with them. So there has been a lot of ideas about how to come up with efficient predictors. And we looked into those, and they basically break apart for task-based parallel programs, because they have not that view. So by using the future information can do much better. So we explore that. And so here is just some data about improvement in execution time normalized to LRU. When we look ahead only, when we also combine it with information that has been collected dynamically by monitoring at the architectural level, and then when we combine it, so this we call radar. It was a paper published last year in HPCA. This is just some data showing that best of breed. This one, there it is. Best of breed dynamic prediction schemes do not work. Seems to disappear anyway. Basically inspired by this, we also looked into what is called global deadlock cache management. So you can take this opportunity of looking into the future one step ahead by saying now we have a multi-level on-chip cache hierarchy, and if it's non-inclusive, you can basically select where to put, when you bring a block into, or a data structure into the cache hierarchy, you can decide whether to only store it in the upper levels or in the lower levels, right? And here again, classical deadlock management schemes cannot deal with that. You would have to have a predictor associated with each of the levels, and they don't interact, and they just create a mess, right? So again, with this limited view of the future, we can do much more intelligent management of a multi-level hierarchy to detect dead data structures, actually. So we call this global deadlock cache management. Was a paper on that published in Computer Architecture Letters early this year. And here is an example how it would work. So we experimented with a number of heuristics implemented at the runtime level. So for example, if we have this data flow graph here, where there are 3 data structures, 4, A, B, C, and D, then actually A would be immediately reused. So here it would make sense to keep it in let's say if we have 2 levels, L2 and L3, in both L2 and L3. Same goes with B, whereas C actually could be replaced, so it would make sense to evict it from L2. We call that shared reuse, but keep it in the L3. And D is not seen here in the limited future view of the limited in the limited view of the future we have, so we would evict it from L2 as well as L3. So we experimented with that. There's a lot of bars here. I'm just going to simplify here to say this is, again, what we have here is the execution time normalized LRU. And as compared to radar, which is this one, we did much better. This is in a non-inclusive cache. All right. How am I doing? I should wrap up. Very quickly, another avenue we have explored for actually, I started to get excited about this probably 50 years ago, something like that, is the fact that we are not using cache hierarchies very efficiently today for a number of reasons. And one reason I'm going to focus a little bit on here is that if you take snapshot of the data that is stored in the cache hierarchy, there will be a lot of values that reoccur, a lot of value locality or redundancy of data values, right? So it really makes sense to use compression to get rid of this redundancy, and that will give the opportunity of improving utilization of caches and memory, which translate into reduced latency, because we can envision much larger last level caches, for example, or much larger main memory to cancel a lot of expensive disk accesses. It could improve the bandwidth between the memory bandwidth, effective memory bandwidth, because we can cancel a lot of expensive last level cache misses, okay? And of course reduce energy consumption, because energy consumption, of course, gets more and more troublesome as we get further away from the processors. So value locality, what is it? Well, using the classical reference locality notion, we can talk about spatial value locality and temporal value locality. Temporal value locality, if we access the same value, it appears in different locations. And spatial value locality, we can explore that if we have values that are close to each other, then you could, of course, encode them more efficiently. So this is one very interesting experiment we did some time ago. Basically, if we have a conventional cache, then we would expect the miss rate to go down as we increase the cache size. But if we think about a hypothetical cache where we only store unique values, distinct values, right? Don't worry about how we should build that, but if we do that, then we can see that we experience much fewer misses, right? For the same size. And in fact, this is very powerful. If we have a 2 megabyte last level cache and this hypothetical, as we call value aware cache, then we could get the same low miss rate for 128K value aware cache as a 2 megabyte conventional cache. And we looked at that for a number of workloads, so we could see a tremendous compressibility potential here, 30 times. And then if I fast forward the tape, we came up with statistical cache compression, paper in ISCA 2014. The interesting thing here is what we do. Essentially, we analyze the value locality on the fly, and then we configure the compressors and decompressor accelerators to match the data. And in fact, what happens is that the value locality doesn't change so often. It keeps stable over time. We don't have to reconfigure this very often. This is a tremendous, very interesting technology. And what we spent a lot of time is, of course, to do the compression, decompression very fast. So it means that we had to go really into the detailed implementation of these engines. And to make a long story short, this was such a great idea, so I mean, it led to no more papers being published, but rather a startup called 0 Point Technologies. So this is on the way to getting deployed. We have packaged it as an IP block sitting between the processor and its cache subsystem and the memory controller to make this go. Okay, back to Stamatis. Stamatis and I, we often talked a lot about new opportunities, and he he said, you know, cache coherence, you should stop working on that, that will not work. But he also gave me a lot of, you know, good thoughts about what he thought was good, what I did. He certainly, some of the things really enticed him, and one of them was actually compression. So I think he would enjoy this part of this talk at least. Also, it's amazing how technologically, how much he did. He was working on the Molen with reconfigurable computing, the SARC project with the accelerators. I mean, it's amazing today. This is really big deal. So, fantastic man. We really miss him. All right. Thank you very much. This was basically the end.
Thank you, Per.